Now, in a previous lesson, we looked at the area under a curve, geometrical area, and we saw how that related to a p-value. We drew a beautiful, nice, symmetric little graph. It colored in 2.5%, 0.025 on either side. You could also do the whole 0.05 on one side. If we got some data points, we did some analysis. The results of those analyses would fall somewhere. We could calculate what the area under the curve was for that analysis. But anyone who's dealt with any kind of data points know it's very rare to find data that looks like that. This is what you're more likely to see. If you were to make a histogram of the finding of some data points for a value, some variable in patients in the ward or in the clinic, this is the kind of spread of data that you're going to see. There's nothing symmetrical about that. There's certainly no beautiful little curve that we can draw over that looks bell-shaped in any form or fashion. So how do we relate this, our actual findings, this is what you'll find most of the time, to this beautiful symmetric bell-shaped curve? Well, the central limit theorem is going to come to our rescue. It's a mathematical theorem and it's absolutely beautiful. I'm not going to do the maths of it, but the beauty really is wonderful and deep. And I want you to have a look at it. Before we get there though, there's some terms that we have to discuss. Just briefly mention them. That would be skewness, kurtosis, because that explains those ugly spread of data points that you're going to see. And then we're going to talk about combinations.